Okay, here we are with chapter 6 in Physics 125. We've covered motion, we covered forces, which are the causes of motion, and now we're going to start talking about momentum. So we got a couple more chapters here in the second unit. Besides the forces chapter, we have momentum, and later on we'll do energy, and we'll do another chapter on forces. And one of the things that we talked about in our chapter on motion was how the motion of the world we live in is often changing, which we call acceleration. Changing motion is acceleration. And that change of the motion is often changing itself. So we have non-constant acceleration. And we talked in the motion chapter, chapter 4, that we couldn't really deal with changing acceleration unless we used calculus, which we're not going to use in this class. So we had to deal with the few examples of constant acceleration like gravity, which has a constant downward acceleration on objects. So the reason we have chapters like chapter 6, momentum, is so that we can get around this problem of non-constant acceleration in everyday problems and still examine the motion. So keep that idea in the back of your mind as we go through this chapter, because sometimes, we talk about how we're going to use the math and how we're going to use this concept, and then the question is, well, why would we do it this way? Well, we do it this way because we get to ignore the acceleration, which is changing and hard for us. So momentum, it's another one of those physics words that you've heard lots of other places in everyday life, but the meaning in physics is maybe a little different. So momentum is moving mass. It's inertia in motion. It's mass that is moving. It's really that first part of Newton's first law. Objects in motion tend to stay in motion. That's what momentum is. When something gets moving in a direction, it's going to keep moving. One of the biggest things I think about when I think about momentum, I think about something like an avalanche, right? Got a whole bunch of snow and ice up on the mountain, and it's sitting still. But once it gets going, it's going to keep going, and you've got to have a really flat space to stop that avalanche from continuing to move forever, because it's built up its momentum. So there's two parts to momentum that you would multiply together to get the value of momentum. It's mass and velocity. And I remember the two parts of momentum myself by thinking about deer and thinking about the chief causes of the death of deer in our area, right? We don't have a lot of wolves. We don't have a lot of coyotes. What kills deer in our area is either bullets fired by hunters, and bullets are able to kill deer because they have very large velocity. They don't have very much mass, but they have a very high velocity, which gives them a lot of momentum, which allows them to kill the deer. And the other thing that kills deer around us is cars. When the deer get on the roads and the cars hit them. So a car also has velocity. You got to have both. If you only have one or the other, you're not going to have momentum. Got to have both. But the car has a lot of momentum, much more because of its mass, right? Very much more massive than a bullet and very much slower than a bullet. So we have this symbol. It might look like a P. It's actually not a P. It's the Greek letter rho. Rho, spelled R-H-O, but pronounced row like you row a boat. It looks like a P, but it does not have a post on it. And it is the symbol of momentum, rho, and it's equal to mass times velocity. So the units are going to be the units of mass, which are kilograms, times the units of velocity, which are meters per second. And because velocity is a vector, our momentum is going to end up being a vector as well. Mass is a scalar. When you multiply a scalar by a vector, you just get a bigger vector. So again, you have to be moving in a particular direction, and whatever direction you're moving in, that's the direction of your momentum. Your momentum is a vector. So we don't just have momentum, we also have a second thing that's called impulse, and how impulse is related to momentum will become very clear quickly, but first we're going to talk about this idea of an impulse. An impulse will change your momentum, and in order to change your momentum, you have to apply a force, and you have to apply it for some period of time, right? If a car comes zooming past you and you reach your hand out and just slap the side of the car, you apply a force to that car, but you don't really change the momentum because you didn't apply a very large force and you didn't apply it for hardly any period of time at all. So it's a combination of how big the force is and how long the time is. And so that's exactly what the equation is. Impulse equals the force, or the average force, what we're going to use in this class, the average force times the time. In reality, in the world in which we live, the force is not constant, right? The force changes. So a good example of this Think of a baseball bat hitting a baseball, right? That's an example of impulse being delivered. So when the bat first starts to make contact with the ball, there's a force, right? There's a push on the ball, but there's not very much push. The ball isn't touching the bat very much. Not very much of the bat is touching the ball, and so the force is small. Okay, but then as the bat continues to swing forward and the ball continues to move backwards, the force delivered gets much larger very quickly, and then the ball begins to move off of the bat. And so as it moves away from the bat can't hit it as hard until finally the ball escapes the bat altogether and moves back in the direction that it came, and the bat can't apply any more force. So we get this changing force over a period of time. And this is a very common shape in nature. It's called a Gaussian distribution. And with calculus, we can calculate the area under the curve. But for us, we don't need to find the area under the curve. What we will do is add up all those forces and divide by how many there are, and we'll get an average force. And if you look carefully, you'll see that the area of this rectangle outlined with the gray dotted lines and the solid black lines, the area of this rectangle, which is very easy to calculate, right? It has a height of force average and it has a width of delta t. That is equal to the blue shaded area underneath the line. You take some of the shaded area here and here, and okay, maybe it's not a perfect picture, but that's the idea. That's how it would work. So one of the things I want to bring out from this graph is that we're going to work almost exclusively in this chapter with the average force, because that's how we're going to do our calculations. But just take a look at this picture and recognize that whatever average force you calculate, the maximum force delivered is going to be quite a bit bigger than the average. Sometimes twice, sometimes 3 or 4 times what the average is. It depends on how long the thing took place and how wide our Gaussian distribution is and how steep it is. But the max is always greater than the average. And so keep that in mind, right? If you calculate the average force delivered to the car is going to be 50,000 newtons, and somebody tells you, well, as long as the force is under 60,000 newtons, the car won't be broken. Remember that if your average is 50, your max is probably going to be well over 60. So the reason we care about impulse is because impulse is equal to the change in momentum. And so this is called the impulse momentum theorem, that the impulse is equal to the change in the momentum. And we're just going to go through a quick algebra exercise to convince ourselves that this theorem is in fact accurate and true, right? I can sit here and tell you, oh, this is the equation, Ft equals delta rho. Ft equals impulse, and delta rho equals change in momentum, mass times change in velocity. I can just tell you that, but we're going to go through the algebra to see why this is so clearly true. And we're just going to do a number of simple algebra substitutions that we've already learned. So the first one is F equals ma, right? Newton's second law, we just talked about last chapter. The force applied is equal to the mass times the acceleration of the object. Or again, more specifically, the acceleration is equal to the force applied divided by the mass of the object. Written a different way means the same thing. So all we're going to do is replace our F with ma. So now we get mat equals delta rho. We rearrange the parentheses, something we're allowed to do because multiplication is commutative. It doesn't matter what order you do the multiplication in. So now we have m times at equals delta rho. And then we go back to chapter 4, where we defined that acceleration is the change in velocity divided by the change in time. So if you rearrange that, bring the t to the other side, you have delta v equals a times delta t. So we take our at and we replace our at with a delta v. And now we have the right side, which has always been delta rho, what impulse is equal to, is suddenly equal to m delta v. And m is mass, and delta v is change in velocity. And that is what momentum is usually going to look like for us, right? Most objects in our everyday life, their mass does not change significantly. I guess when you drive down the road, you burn some gasoline, and so your car's mass gets a little bit lighter, but compared to the total mass of the car, that's a very minor part. So we are almost always going to be talking about the velocity being the part of momentum that changes, right? When we talk about balls, when we talk about bikes or something like that, it's the velocity that changes, not the mass that changes. Now, you can get situations where the mass changes. That's what rockets are, right? When we built those rockets to go to the moon, they were 40 stories tall, and in the end, those 3 astronauts rode in a little capsule that was probably smaller than our lecture hall. So what was in the other 39 stories? Well, the answer is there was a whole lot of fuel. So as that rocket took off, and that rocket fuel was burned to provide an impulse and a change in momentum, not only did the rocket speed up, but the rocket's mass also got smaller, so that caused the velocity to speed up, increase even more. But that's rocket science. That's why they call it rocket science. It's not easy. Again, that requires a calculus calculation, which is beyond the scope of this class. So what we've learned in this slide is simply that the impulse momentum theorem does clearly state that impulse, also written as Ft, is equal to the change in momentum. And so we'll look at a couple of example problems of this, but this is how life stays interesting, right? Momentum is not interesting by itself. An object going down the road, object's in motion stays in motion. It'll go flying by you, nothing will change. Why is this interesting? Well, when a force is applied for a period of time, then the momentum changes and things get interesting. So the impulse momentum theorem is one of the first important equal signs we're going to have in this chapter, in which we're going to have some of the information from one side and all the information from the other, and that will allow us to solve the problem. But here are some really basic problems, not even combining the momentum and the impulse, just doing them separately. So what would the momentum of a baseball be if its mass is 0.15 kilograms and its velocity is 15 meters per second? Again, remember, in these lectures, anytime we have a problem, you should pause the video, do the problem yourself, and then restart the video to see what the answer is. But you need that practice. You need to attempt it yourself so that you get that practice of trying to solve the problems. You learn way more if you attempt the problems than if you just watch me do them all the way through. So it's just momentum equals mv, 15 times 15 with a decimal point. So we put that decimal point as 2.25 kilogram meters per second, right? We combine the units of the objects that we're multiplying together. So what is the speed of a 2,000 kilogram car if it has 8,000 kilogram meters per second worth of momentum? So this time, what is the speed? So we're asked for the velocity, we're given the mass, and we're given the momentum. So how do we go about doing that? Again, it's a simple three-variable problem. We have two of the variables, this time rho and m. Last time we had m and v, and we were solving for rho. So we want to solve for v, so we divide both sides by m. We get v equals rho over m. And now we can plug in our numbers. 8,000 divided by 2,000 gives us a velocity of 4. The kilograms drop out, and we're left with units of meters per second. So final practice problem is about impulse. So what impulse is introduced by a 450 Newton force applied for a half of a second? So this time we're given a force and we're given a time, and we're asked for an impulse. So seems pretty straightforward. Impulse equals force times time. That was our definition. We're given a force, given a time. We plug them in, we multiply them together, and we get 225 newtons times seconds. But then we ask ourselves, wait a second, he said impulse was equal to change in momentum. Momentum has units of kilogram meters per second. So are Newton seconds and kilogram meters per second really the same thing? I mean, if this equal sign is real, then the units have to be the same. Is that correct? So we're going to take a moment and examine these units and remind ourselves what a Newton is. Remember, it's a fairly new unit. We just learned it last chapter. What is a Newton actually? A Newton, as we remember from F equals ma, the Newton, which is what force is measured in, is equal to the units of mass times the units of acceleration. So mass is kilograms, acceleration is meters per second squared. So we can substitute in for a Newton, kilogram meters per second squared, anytime we need to. So if we do that up here, we get kilogram meters per second squared for the Newton part, and we get seconds over 1 for the seconds part. And so what do we see? We see that the second in the numerator will cancel out with one of the seconds in the denominator, and we will get kilogram meters per second being equal to Newton seconds. So that's what we wanted to see if it was equal to. So we have done the algebra now with the units, with the derived unit, and shown that those are in fact the same thing. So the impulse momentum theorem holds on a unit basis as well. But again, we have to remind ourselves that in order for that to hold, we have to follow a couple of rules, right? Our force always needs to be in newtons, not in kilonewtons or millinewtons. Our time always needs to be in seconds. And then on the momentum side, we need to have our mass in kilograms, not grams. and our velocity in meters per second. So as long as we follow those rules, this equal sign will work and the units will line up, and we won't have to do any strange conversions in the process of going from impulse to change in momentum. So there's a couple of cases that most interesting momentum problems fall into. And the first case is the case of increasing momentum. So that's when we want to give something momentum. Maybe it's at rest, maybe it's already moving, but the point is we want it to move more. This comes up a lot of times in sports, right? A lot of our sports revolve around balls, and generally you want to make the ball go really fast, whether that's because you need to slip it past a goalie, or whether you want it to go really far and over the fence, or whether you want to slip it past a batter. Whatever the case is, you want the ball to go fast, which means, since the ball's mass isn't going to change very much, you want the momentum to be very large, because a large momentum means a large velocity. So again, you can think of lots of examples, but the details of how you get good at almost any sport lie ultimately in this task of increasing the momentum. And the physics of it is very simple, right? You increase momentum, you change momentum by using an impulse. Impulse is force times time. So if you want to make the impulse bigger, you got to make the two parts that go into the impulse bigger. That's bigger force and bigger time. Now, there are times when a bigger force is not ideal, right? I'm sure you've maybe had the experience of being in a baseball game and you want to hit a home run, and so you swing that bat super, super hard, and of course you miss the ball. So sometimes you got to sacrifice a little bit of force for the sake of control so you can actually make contact. But the goal is to hit it as hard as you can. Hit it, of course, being part of the key, but hit it as hard as you can, and then as long as you can. And your coach never tells you this is physics, but this is physics. The long part is the really important part, and that's why you follow through. That's why you're taught to follow through. Taught to follow through in baseball, taught to follow through in throwing a football, throwing a baseball, serving a volleyball, spiking a volleyball, smashing a badminton birdie, bowling a bowling ball, all kind of, think of any ball sports you can think of, and the principle is follow through. And the idea of following through is that your force will be applied for a longer time, your impulse will be bigger, the velocity of the object will be larger. That's what you're going for in all of those cases. One of the things that can really drive that principle home, and this is very common in physics, is if you want to test a principle, think about the opposite situation. What do you do in sports when you don't want the ball to go really fast, really far, right? What happens when you're bunting in baseball, right? Do you follow through with the bunt? No, you kind of hold the bat out there, you let the ball bounce off the bat, and you drop your bat and you run to first base. So you don't follow through because you don't want to hit the ball very hard, because you don't want it to get all the way back to the pitcher in time for him to throw you out at first base. You're bunting for a single. Or say in badminton or even in volleyball, more so in badminton than volleyball, you're hitting the badminton birdie back and forth, and you hit one to the back corner, and then you want to just barely tap it over the net, so they have to run forward and hit it, right? So they call it, when I was in gym class, they called that a dink. So you hit it with your racket, but you don't follow through. You just kind of put your racket up there and let it bounce off your racket, and it doesn't go very far, falls just over on their side of the net. So you can think of that in a lot of different situations, right? When you're setting in volleyball, you're not trying to hit it a long ways, you're trying to set it to a very specific location, and you don't follow through in the same way as when you're trying to spike the ball. So just drives home the idea of not having a long time when you don't want it to go very far. Yeah, I think that's all I need to say for that one. The second case is in many ways the exact opposite of the first case. So in case one, the object was sitting still, or maybe not sitting still, going slow. We want it to go a lot faster. Case two, something is going very fast, and our goal is to stop it. Our goal is to stop it. So this is decreasing an object's momentum. And this is one of those things where you don't have a lot of choice, right? The object is flying towards you at high speed and you need to stop it somehow. And generally you know, maybe you don't care, right? Somebody throws a rock at you, you know, you duck, the rock hits the tree and the rock stops very fast, and it hurts the rock, but nobody cares. It's a rock, right? Rocks don't break. We're talking about stuff that we don't want to break. We want to stop it in a gentle way. We don't want the thing to be ruined, right? I just talked a few slides ago about that graph, and how the maximum force is going to be much bigger than the average force. So what can we do? And interestingly, although we're doing the opposite thing, the solution is exactly the same. If you want to deliver a really big impulse, you need a big, long time, follow through, hit that baseball as hard as you can for as long as you can. If you want to stop the baseball in a gentle way without hurting your hand, the same solution is available. Increase the time. Because see, this time, the momentum side of the equation is already fixed. The momentum side, that rho value is already 5,000 units or 10,000 units or whatever it is. So this time, by making the time bigger, that allows the force to be smaller, right? You can think about that math. So we got 5,000 units and we're going to stop it in a half of a second. Well, that's going to require a large force, right? What do we have to multiply by half to get 5,000? Well, we got to multiply 10,000 by half to get 5,000. But on the other hand, if I can find some way to deliver my force over a longer period of time, say 5 seconds, well, what do I have to multiply by 5 to get 5,000? Well, only 1,000. So I can use 10 times less force if I can use 10 times more time. So that's the principle of decreasing momentum. And one of the examples I think that is most real to me, and maybe would be real to you if you had this experience, is if you've ever had played in a water balloon toss or an egg toss, right? Where you have a water balloon and you have two partners and you stand, 2 foot apart, and you toss the balloon to the other person, and that's easy at 2 feet, right? They can easily catch it. You don't have to throw it very hard. It's not moving very fast. They catch it, but then you're supposed to take a step back. And they throw it to you and they take a step back. And pretty soon you're 10, 15, 20 feet apart, and you're trying to throw this water balloon hard enough so it gets to your partner, but then your partner's got this fast moving water balloon that they got to stop in a gentle enough way that the water balloon doesn't burst. So what do? How do you catch a water balloon? Well, you put your hands forward as it comes towards you, and then as it comes into your hands, you move your hands backwards with the balloon. And that gives you more time to stop the balloon. You don't want to catch the water balloon like a first baseman catches a throw, right? You don't want to have your hand extended, your elbow locked so that the balloon's going to hit your hand held up like a stop sign, because that's going to burst the balloon and shower you with water, or with egg if you're playing with a raw egg. You don't want to catch it like that because there's not enough time for it to stop. Now, a first baseman's trying to do something different, right? He's stretching out, trying to catch that ball as quickly as possible because the runner's coming down the line and he wants to get the out. But if you think about somebody else on the baseball diamond, the catcher, what does the catcher do when that crazy pitcher winds up and chucks a ball at him at 100 miles an hour, right? He holds his arm bent in front of him, and as the ball enters his glove, his hand moves back toward his chest, and his glove is thicker and has more padding. That's exactly what padding does, right? Think about any situation where there is padding, whether it's padding. My kids are rollerblading right now. Whether you have elbow pads or knee pads for rollerblading, or whether you have padding on the ground after a high jump in track, all of the purpose of that padding is so that when something hits that padding, the padding can collapse and the object will have more time to do its stopping, and therefore the pad can deliver a smaller force than if you fell directly on the concrete. Concrete doesn't have any give, right? Concrete's not going to collapse for you. So when you fall on concrete, it delivers the force kind of all at once. You get a big force and you get stuff breaking, right? This guy in the picture, right, he slammed on the brakes. The brakes stopped the truck in a relatively gentle way. We have anti-lock brakes, which will squeeze and release so that they can keep taking away momentum from the wheels without them locking up. But his big block of stone inside of his truck was not secured, and so there were no brakes on the stone. It kept moving when the truck stopped, when he slammed on the brakes. This is ultimately what we do in our cars as well. And to draw this for us. So when we got drivers in vehicles, and this is a great example of the need to decrease momentum, right? We like to drive fast. It gets us places very quickly. Again, this recently I was able to travel to visit some family, and they live hundreds of miles away, and we are very appreciative when you have little kids in the car that you can travel at 70 miles an hour and you can cover hundreds of miles in a relatively few number of hours, because the kids get impatient. But when you are traveling that fast, you run the risk, right, of what happens if this car needs to stop suddenly. And again, the car is the car. Car doesn't have feelings. Car's not alive. If the car gets smashed up, the car's smashed up. But the people inside the car we care about very much, and people are a lot more delicate than cars are. So how do we stop the people? And of course, the first thing that they invented was the seatbelt. And you might think that a seatbelt is just a rope that they stretch across your waist, but it's really not. It's a lot more flexible than that, and it's a lot wider than that. We'll talk about pressure a little later, about why a wide band seatbelt is going to be better than a thin, piano wire seatbelt. But it also has a fair amount of give. So when you slam on the brakes, that seatbelt gives some. Doesn't feel like it. Feels like it slams into your waist and stops you immediately. But there is give to it to allow your body to stop more gradually. And a lap belt will stop your lower body. And then if you're wearing a shoulder strap, that will stop your upper body. But unfortunately, there's another hinge here, and we have a head, and our head has our brain in it, and that's kind of important. And we need to make sure that our brain is stopped gently as well. It doesn't do any good to safely stop our body and then have our head slam into the windshield or into the steering wheel and give us a concussion inside of our head, and that can be fatal or can cause brain damage or all kinds of things. So rather than have a seatbelt that would mess up our hair and make it difficult for us to check our blind spot, they came up with something called an airbag. And airbags are really a marvel of modern science, and there's a whole lot of physics and chemistry in the airbag. Ultimately, there's a little sensor in the front of your car, and this sensor, it sounds real fancy, it's a sensor, right? Well, really, it's just a chunk of iron that's attached to some springs, and it's got a big fancy name. It's called an accelerometer. But really, all it does is it measures your acceleration, right? And all they do is when they first build the car, they slam on the brakes and they see how far this metal will go forward when they slam on the brakes. And if they, test it 100 times and it never goes any further than this, then right beyond that, they put a switch so that if your car ever stops fast enough for that piece of metal to hit that switch, then they know your car is stopping faster than the brakes can stop it. Well, when your car is stopping faster than the brakes can stop it, that's another way for saying your car is crashing. That's what's happening. Your car is crashing, and that is when the safety features really need to kick in, right? So there's this switch, and when the mass hits that switch, then we call it the airbag sensor, right? It sends a message to the airbag, which is inside your steering wheel, and your airbag blows up incredibly fast, right? The car is already crashing. The front of the car is already crashing. Sometimes I ask my high school kids, why don't we have airbags for the car? Why don't we have a big balloon that blows up in front of the car and protects the car, right? Cars are expensive. Wouldn't it be nice to not have to go to the body shop after a fender bender? And the answer, part of the answer is, again, we care less about cars, care more about living beings. But part of the answer is also that we wouldn't know when to deploy the airbag, because the car has to be crashing already before we know to deploy the human airbag. And that means that the human airbag has to blow up super fast, faster than a fan could blow it up. And so we actually have a chemistry reaction, a highly catalyzed chemistry reaction that occurs in very small fractions of a second. I'm not sure what it is, whether it's microseconds or nanoseconds, because it's only going to take a few milliseconds for the crash to get from the front bumper to the person. But it blows the bag up very quickly. But it's not blown up like a balloon, not blown up and sealed, right? I've had the experience of getting hit by a sealed balloon before, and you think balloons are soft. Well, if you get hit by a sealed balloon, you find out balloons are not very soft. But it blows up and it has holes in it. Even as it blows up, those holes are open and some of the gas escapes. And the holes are there so that as your face goes into the airbag, you can push the air out and the airbag can continue to stop you through the whole width of the airbag. Now, in order for the airbag to be functional and correctly functional, your head needs to be back to begin with, right? If your head is too close to the steering wheel, Then as the airbag blows up, it throws your head backwards, and that's not healthy for you. So keep your head back against the headrest. Keep your hands at 10 and 2 or 3 and 9 so they're not in the way of the airbag. Wouldn't want a hand or an arm slammed into your face by the airbag either. That would be pretty unpleasant. And now we have other airbags, right? Side impact airbags and different types of airbags with their own accelerometers that measure sideways motion of your vehicle and all those sorts of things. And the whole idea is to keep you as the precious cargo of the vehicle in such a way that you can be stopped slowly. And the key to that ultimately, as we've already said repeatedly, is time. Extend the impact time and we will cause you to be stopped with a smaller force that will cause less damage. Here's just it represented with pictures, right? Here's the truck running into a haystack. The haystack is able to stop the truck without causing much damage because the hay stops it slowly over a large period of time. On the other hand, when the truck runs into the wall stops it very quickly and you get an accordion truck. One of the things I'd like to drive home about this picture is to emphasize the fact that in both cases, the truck had the exact same momentum. Airbags, none of these things cause you to have less momentum to start with. You have the same initial momentum. That's not the point. We don't have any control over that. The point is that we are going to get rid of that same amount of momentum with a lot less force if we have a lot more time. The example, like the numbers I used before, right? 5,000 units, if we stop you in a half a second, we need a force of 10,000 newtons. 5,000 units of momentum, if we stop you in 5 seconds, we only need a force of 1,000 newtons. That's a lot less force. But in both cases, you started with the same 5,000 units of momentum. And here it is with graphs. Again, these are those same Gaussian distribution graphs that we saw at the beginning of the lecture. But the seatbelt, again, extends the time. And by extending the time, it decreases the average and the maximum force necessary. On the other hand, if you have no seatbelt and then you wait for the dashboard to stop you, that's going to happen in a very short period of time, and therefore the maximum and the average force will have to be much higher. So now we're going to do a couple of these momentum problems, momentum impulse problems. So if we have a baseball and it's pitched at 35 meters per second and it's hit so it leaves the bat at 45 meters per second, what was the impulse delivered to the ball? So we are given a mass and a couple of velocities, but we're asked for an impulse. So go ahead and give it a shot, see what you get. All right, how many of you got an answer of 12? Can't see any of your hands. We're not in class together, but typically 60 to 80% of my students get 12 the first time they do this problem because they say, hey, N delta V, right? Impulse equals change in momentum, N delta V. I got 45, I got 35, subtract them, I get 10. 10 times 1.2 is 12. The answer must be 12. The answer is not 12 because remember how baseball works, right? Baseball works, the ball goes in, hits the bat, and gets thrown back out. So the baseball leaves the bat going the opposite direction that it came in from the pitcher. So we got to pay attention to the direction of things. And in this chapter especially, we're going to keep track of that with signs, right? Positive and negative signs. So it's not that 35 and 45 are wrong. It's just that one of those numbers has to be negative because it's in the opposite direction of the other. And once we get the impulse, we're going to ask ourselves if that impulse was delivered in 0.15 seconds, what force was applied. So we're going to move on to the next slide and see how to do these problems in the correct way. So again, the first problem, we have the impulse equal to the change in momentum. That's the equation that we need. So we break up change in momentum. That becomes mass times the final minus the initial velocity, right? Remember, delta always means changing. And in this case, the mass isn't changing, it's the velocity changing. So delta rho becomes m delta v, and delta v becomes v final minus v initial. Now, we have to decide in the problem what direction is positive and what direction is negative. So I decided to do this problem such that Left was positive because that's the direction the ball was going with to begin with, and right was negative. Okay, now that's backwards of the Cartesian coordinate plane. I understand that, but it allows my initial value to be positive, which is something we prefer sometimes. It's not important which direction is positive and which direction is negative. What's important is that you are consistent throughout the problem and that you correctly interpret your answer. So the ball comes in at 35 meters per second in a positive direction. So I put in 35 positive, but we're subtracting 35. So we're subtracting a positive 35. But then he hits the ball and it goes back in the opposite direction, which is now going to be counted negative because we decided left was positive, so right is negative. So our final velocity is negative 45, right? Because the bat really has to first stop the ball, right? It's got to go from 35 down to 0, and then it's got to go from 0 back up to 45. So it's not really only changing by 10 meters per second. It's changing by 35 and then 45 in the opposite direction. So when we do that, negative 45 minus 35, we get a total change in velocity of negative 80. Negative 80 times 1.2 gives us an answer of negative 96 kilogram meters per second. Now you might read that and think, well, that's weird. How can you have a negative momentum? Well, remember, momentum is a vector, and in this case, the negative sign is simply telling us the direction of that vector. Now we decided toward the catcher was positive and toward the center fielder was negative. Now when that batter swings his bat, what direction is the impulse of his bat going? Is it going toward center field, which would be negative, or is it going toward the catcher, which would be positive? So we realize, well, of course, he swings towards center field, so his impulse should be a negative number. And likewise, as we go on here to figure out what force was applied, if he hit the ball in the course of 0.15 seconds, we're likewise going to end up with a negative force because his force is towards center field. The force of his bat is towards center field as well. So here we have the other definition of impulse, right? Impulse is equal to change in momentum. Impulse is also equal to the force times the time. We have an impulse now from the previous part of the problem, and we were given a time. So we're just going to divide our force times time, divide it by time, so the time drops out. So we have force equal to impulse divided by time. And now we just plug our values in. Negative 96 kilogram meters per second divided by 0.15 seconds. That's going to end up giving us seconds squared in the denominator. A kilogram meter per second squared is a newton. So we end up with a force that's 640 newtons. And I just made a big deal about it being negative, and it's not. So I forgot my negative sign. This is the magnitude of the force. It's the size of the force. It doesn't tell us the direction. The direction is towards center field. Obviously, if you take a negative divided by a positive, you should get a negative value. So one of the things that comes up when we discuss momentum is the idea of bouncing. What happens when something bounces? Well, bouncing matters, and it matters a lot. And why it matters comes out most clearly in a momentum discussion. So here we have a stuffed bear and we have a rubber ball, and they're the same mass, and we drop them from the same height, and so they're going to strike the ground, both going the same speed. But that's where things are going to change, right? They both strike the ground at the same speed. They have the same mass. It's mv and it's mv. But our teddy bear is stuffed full of, beanies or sand or whatever. And so he just plops and stays there. Whereas the rubber ball hits the ground and bounces back. So what's going on? So for the teddy bear, we have the mass and we have a final velocity of 0 and an initial velocity of negative v, because down is negative, right? So we're subtracting a negative. So the teddy bear had a change in momentum of mv, okay? But for the bouncing ball, we've got m. He heads up at v, which is positive, minus his initial velocity, which was going down, which is negative. So it's v minus negative v, which turns into a positive sign. So v plus v is 2v. So the change in momentum for the rubber ball is 2mv. So that means that the ground delivered twice the impulse to the bouncing ball than it did to the teddy bear. Now the ground can handle that, right? The ground is very strong, and we don't feel the recoil of the earth, and that's not a big deal. But there are lots of other circumstances where that bounce has a much greater effect, right? And one of those places is in the energy industry, where you have a hydroelectric plant and the water is coming down from behind the dam, And they design the blades of those water wheels such that the water hits them and effectively bounces off. And that delivers a greater impulse, consequently more energy, which we can turn into electricity. But also lots of other everyday examples of where a bounce is going to result in more energy delivered. You can set up a little experiment, right? Build a little tower out of blocks and then throw something at the blocks that will bounce off and throw something at the blocks that will not bounce off. And you will see that the bouncing object knocks the tower over more effectively, sends the blocks scattering a little further. What I would do in class if we were there is I'd open one of our doors and I would throw a baseball at the door, and then I'd throw a clump of clay that has the same mass as the baseball at the door, and the baseball would be able to open the door further because it would bounce off more effectively than the clay. So a bouncing delivers a greater impulse. That's what we need to understand. A greater impulse is needed to bounce something than to just stop it. So we got impulse momentum problems, which we've already kind of talked about with the baseball, and we'll do some more examples a little later. But then we have this discussion of just the momentum. And to understand that, we need to talk about what systems are. We design systems in science. Again, we try to study nature, and nature is really, really complicated. And there's a lot of different pieces to nature. And so it's very hard to study. So what we do is we simplify it down. We simplify it down and we study just one little section of the world at a time. And we try to learn something from that section and then apply it to the world at large. And so that little section we call a system. And so we have some rules about systems. First of all, we get to define what our system is. Our system could be something as simple as a ball and the ground, right? Where we were looking at the ball bouncing, that could be a system. Or it could be more complicated than that. But the goal, again, is to learn something from the system that we can apply more generally to the universe. The Earth is a great example of a system, right? We look at the Earth and we focus on the interactions within the Earth. We don't focus on how the Earth interacts with other stuff. We're going to do a number of systems in this class, in this chapter, of two cars colliding with one another on a low friction track or something like that. In chemistry, you might have studied a container of gas when you were learning about gas laws, and you had a sealed container of gas whose temperature was going to increase or decrease or something. So you have gas in a closed container, and that's the system you're looking at. In order for this to work well, what we need for our system to do is to be closed and isolated, right? If we're letting stuff come in and out of our system all the time, then it's pretty hard for us to draw any quick and easy conclusions. And whether that's actual stuff, matter entering or leaving our system, or whether that's forces entering or leaving our system, both of those can screw things up. So what we would like is a closed, isolated system. Unfortunately, we pretty much never get that, right? Even something like the Earth sitting in the vacuum of space is not really a closed, isolated system. We have asteroids that strike the Earth, adding mass. We have a light coming from the sun, which gives us energy. We have a gravitational force from the sun pulling on us, which is a force. But still, it's one of those cases, like we talked a little earlier about how a car driving down the road is burning some gasoline. So its mass is decreasing a little bit, but its mass is decreasing by, a few hundred grams, and it has a mass of several thousand kilograms. So it's a small enough difference that we can go, it doesn't really affect things. So we want an approximately closed and isolated system. So if we have a closed and isolated system, or an approximately closed and isolated system, and we're going to study the momentum in the system, we've already discussed the fact that momentum changes when we have an impulse. And when we have an impulse, we have to have a force. And we learned last chapter that when we have a force, according to Newton's third law, we always have a pair of forces. Forces don't ever exist on their own. They always come in pairs. And that pair force is just the same size, but is in the opposite direction. Remember, the horse pulled on the wagon with 1,000 newtons. The wagon pulls back on the horse with 1,000 newtons. So object A exerts a force on B, and object B exerts a equal force, but in the opposite direction. That's what the negative sign is for. Opposite direction. If I push left, it pushes right. If I punch the wall pushes back on me. But same size, so this equal sign. They're the same size. The only difference is a sign, right? One's 120 newtons, the other's negative 120 newtons. So if we want to make them equal to each other, we need to add a negative sign to cancel out or to give the second one the same negative sign. Now, in impulse, there's more than just force. There's also the time, right? So we have to start looking at the time that a force is delivered. So now we have to ask ourselves, can object A exert a force for a longer period of time than object B exerts back? And we quickly come to the conclusion that if we allow A to do its force longer or shorter, then we've violated Newton's third law for part of the time, right? There would only be one force instead of two. So the times must also be equal. And if we have forces that are equal and opposite and times that are exactly equal, well, then we're going to end up with impulses that are exactly equal and opposite, right? Forces are the same size, times are the same size. The only difference is this sign that indicates the opposite direction. So now our impulses are equal and opposite, and therefore our changes in momentum are also equal and opposite. So within our system, if car A bumps into car B and gives it some of its momentum to the right, car B is going to give car A some momentum to the left, and it's going to be exactly the same amount that's going to be given. And so this very quickly leads us to this idea of conservation of momentum, which I'm sure you've heard of this before in chemistry classes and other science classes. It's one of the principles about the universe that we've figured out, that stuff is conserved. It's not created. It's not destroyed. The same amount is there. We just have to figure out where it went. And we use this in mass, we use this in energy, we use this in momentum, we use this in charge, we use this in a lot of different areas of science, but you've probably experienced it before in chemistry, or if you took a biology class when you're talking about the leaves getting energy from the sun and the ATP and the photosynthesis process. You have to account for all the energy. That's energy conservation. So in the closed isolated system, we find that the total momentum is conserved because although object A can pass it to object B, object B will pass an equal and opposite amount in the other direction. So whatever momentum we have is going to get passed around potentially, but the same amount will be there. I find this to be much more effective when I talk about the example of money, right? We can all imagine being in a room with a fixed number of people. How many people is not important. And the people all have some money. And how much money isn't important either. The point is that somebody locks the door and we're all stuck in this room. And we have money and we have nothing else to do. So we start playing rock, paper, scissors for $1 a game. And some people win and some people lose. And money gets transferred around between the people. But the net worth of the room doesn't change, right? There's the same amount of money in the room the whole time. And even if someone says, "Oh, I'll write an IOU," then they're negative money, and somebody else has money beyond the total or whatever. But the point is, you have the same amount of money in the room. It's been conserved. There's no winning, no losing, no there's transfer, but there's no total change in the amount that we have. So that's the idea of conservation. And of course, that's going to lead us to an equal sign, right? It's going to lead us to this idea that whatever momentum we had at the beginning is going to be the same we're going to have at the end. And whether we know the beginning or the end, we know that the total stays the same throughout the entire process. And again, this is going to be helpful because what we're going to start doing is studying collisions. We're going to study things that crash into each other. When they crash into each other, there's all kind of weird forces and weird accelerations that are not constant. But no matter how funky the crash is, the total momentum before and the total momentum after have to be equal. So we can look at masses and velocities before, and we can predict masses and velocities after without having to look at the details of the collision. So it's going to be all about before and after. And this little a, little b, little c, these are just the different objects in the system. We might have two. We usually don't have one. One's pretty boring. Object has momentum. Afterwards, object has the same momentum because all of the momentum's in the same object. But we'll do a lot of systems with two objects, just A and B. We might do a few with three objects. But whatever the momentum of object A plus B plus C is before, we'll get some total. And then afterwards, we've got a new momentum. That's what these little tick marks are. They're prime marks. It just says that it's different. It's still the momentum of A, but it's different from the first one because we've had a collision and velocities have changed. So this is how this works. So we got a bumper car, a couple of bumper cars. Bumper car A is going 15 meters per second with a mass 355, and it crashes into the back of the second bumper car, which is a little more massive, but a little bit slower. So if car A ends up going just 12 meters per second, how fast did car B end up going? And what was the total momentum of the two cars collision system before the collision and after the collision? So this slide shows us, big words of the whole problem, so you can get all the numbers down. On the next slide, we'll see little words, and then we'll see how to do the problem. Again, I would encourage you to take a shot based on the equations on the previous slide on doing this problem yourself before you watch me do it. So there's the problem up at the top. First thing we got to do is create an equation for the total momentum before and another for the total after. So it's that same equation, right? It's just the total before is car A plus car B. The total after is car A new plus car B new. And the momentum equation, just to remind us from the beginning, is mv. So now we plug in our numbers, right? Car A had a mass of 355 and a velocity of 15. B had 450 and 11. So we got all the numbers for the before. So we can stick them all in. We can multiply. We can add. This is just arithmetic, right? And we get this is our total. So that actually answers our second question. What's the total momentum of the two-car system before the collision? It's 10,275 kilogram meters per second, 10,275 units of momentum. So that's the first answer that we figured out just by plugging the values they gave us in. But the real question we're after is how fast was car B moving afterwards? So afterwards, we've got the masses are the same, and we've got one of the velocities, but we have an unknown. Okay, so as we write this out, we see, well, we don't know velocity of car B's new velocity, but we also don't know the afterward momentum. So it looks like we have two unknowns. But the reality is we don't, because of momentum conservation. We can take our value for the total momentum before and we can stick it in as our value for total momentum after. So we actually have a value for this one. It's this number in yellow. And then we'll only have one unknown and we can solve algebraically. So we do the 355 times 12, we get this 4260. We subtract the 4260. And that leaves us with 6015 divided by the 450, and we get our velocity of B as 13.4 meters per second. Now we can go back with this answer and take a moment and ask ourselves whether it makes sense, right? This was a rear end collision. Car A was going 15 and it ran into the back of car B, which was going 11. So the back car was going faster and it crashed into the back of the front car. So afterwards, we would expect the front car to be going faster, right? Otherwise, they would still be stuck together, or car A would somehow have gone through car B, which that can't happen. So we expect car B to at least be going faster than car A, which was 12, and we see 13.4 is faster than 12, so it is what we would expect. So here's another example. Again, we're just going to work through a couple of examples to give ourselves some exposure to this, see how different types of problems work. This one's a little different. This time we have a bullet going very fast, crashing into a stationary block of wood. And what is the final velocity of the block of wood with the bullet stuck in it? And as we're going to talk about in a couple of slides, this is a different type of problem. Sometimes when things collide, they bounce off like the bumper cars did, like a baseball bounces off of a bat. But sometimes when things collide, they stick together, and that makes the problem a little different, actually a little easier, but a little different. So there is a little bit of a challenge here because they gave us the mass of the bullet in grams, and they gave us the mass of the block in kilograms. So we got to get those things straightened out, get them in the same units, which of course we would like kilograms. So there's 2,000 grams in a kilogram, so we're going to multiply by 1 kilogram over 1,000 grams, so we're going to end up dividing by 1,000. But again, we write that same equation. The total momentum before is going to equal the momentum of the bullet plus the momentum of the block. But the total momentum afterwards is just going to be a single momentum because the bullet and the block are now stuck together. So they're going to have to be going the same speed because they're stuck together. So there's only one term afterwards. There's two terms before, only one term after. So we take all the information from the before, which is what we were given, the mass of the bullet converted to kilograms, the velocity of the bullet, the mass of the block, and the velocity of the block. Initially, it's stationary. So stationary means not moving. So that gives us a velocity of 0, our favorite number. Anything times 0 is 0. So we just got to multiply those two together and we get a total of 13.1. So 13.1 is the total momentum before, which means it will also be the total momentum after. Afterwards, we only have a single object. That single object has both the mass of the bullet and the mass of the block together. So we have to add the masses together, multiply it by a velocity that we don't know, and it's equal to that same total because the total before equals the total after. I'm going to say that a lot of times. It's really important. It's what the principle of conservation of momentum tells us, and it's what's so useful about the idea of conservation of momentum. So then we take our momentum, we divide it by our mass, and that gives us our velocity. So yes, the bullet has slowed down significantly, but it has also increased 100-fold in mass by getting stuck in the block. So that's understandable. So those two problems, I don't know if you noticed or not, but everything in those two problems was moving in the same direction, right? There was a rear end collision, so both bumper cars are moving in the same direction. The bullet slammed into a block that was stationary, and then the bullet in the block kept moving in the direction of the bullet. Now we're going to do a problem more like the baseball problem that we did in the notes, where things are moving in opposite directions. And this is a very realistic situation. And again, it means we have to keep our signs straight. So this time we have pool balls. A couple of pool balls. They have the same mass, so that's going to be kind of easy. But one is rolling left and one is rolling right. And because of that, we're going to have to pay attention to our signs. And if we don't pay attention to our signs, we're going to get the problem wrong. So we really want to pay attention to our signs. We're given both of their velocities initially and one of their velocities afterwards, and we're asked for the other one. So you'll notice the questions aren't, there's not a huge variety of questions that you're going to get asked. You're going to tend to be, the question is going to tend to be, what about the velocity afterward of one of the objects? That's the power of conservation of momentum, to be able to predict what's going to happen after a collision. So same approach, we're going to write the momentum before and the momentum after. We got a blue ball and a red ball, so blue plus red before and after. We're going to plug in the information that we have. We're going to decide this time that that left is positive because that's what we decided to do. Again, it was the first velocity we came to and it was going left, so we decided left was positive in this problem. So it's got a mass of 0.6 and a velocity of 6, so 0.6 times 6. But the red one is rolling to the right. Well, if left is positive, then right must be negative. So I got a negative sign in front of that 4. So this comes out to be 3.6, and this comes out to be negative 2.4. So when you add those together, you're actually going to subtract because one of them is negative, and we get a total of just 1.2, okay? Because they were rolling in opposite directions. If you consider the momentum of the whole system, with one rolling left and one rolling right, they're canceling each other out, and the total is smaller in size than either of the individuals is, okay? Got to be able to wrap your brain around that and accept that that is going to be true because of the different directions of the two balls beforehand. Now, afterwards, they're both moving independently as well, right? Pool balls don't stick together. They bounce off of one another. Afterwards, the red one is rolling left. Well, left is the positive direction. So here's the red one. He was rolling right. Now he bounces and goes away to the left. My colors are reversed. Oh, well. That's not important. The red one goes back in the opposite direction. So it goes from a negative value to a positive value. And we don't know what the blue one does. That's what we're trying to find out. So we set those, add those up. They're going to add up to that same total we had beforehand. So we get 1.8 plus 0.6 velocity of B afterwards equals 1.2. So we got to subtract the 1.8 across, and we end up with a negative value. We divide our negative value by 0.6, and we end up with a negative velocity, which again is what we would expect. If they come from different directions and they crash into each other, we would expect them to move off in opposite directions. The red one was moving left, which is positive, so we're going to expect the blue one to move to the right in the negative direction, and that's what we get. Now, telling me the answer is -1 meters per second is not the best way to answer the question. We use negative signs and positive signs to indicate direction. But you will notice there have been several problems where I've just decided what direction is positive, what direction is negative. I'm allowed to do that. I'm the one doing the problem. But I need to communicate to the person who asked the problem in the same language that they asked the question in. I need to communicate the answer in the same language they asked the question in. So if the question had said, pool ball, the blue pool ball is moving in the positive direction at 6 and the red is moving in the negative direction at 4, then it would be fine for me to say -1 meter per second. But because they used left and right, I should translate my signs back into the directional language of the problem. And I should finish this problem by saying the blue ball moves 1 meter per second to the right. That way there's no confusion. If your teacher chose a different direction to be positive than you did, there's no confusion when they grade your answer. Because if you answer in the language of the problem, they can't possibly object to that way of answering because you're using the information they gave you. So I referenced this a little bit earlier, but there are two different types of collisions. One is called an elastic collision. This is when the objects bounce off of one another without any damage to the objects, without any generation of heat. Perfectly elastic collisions. Momentum is conserved and kinetic energy is conserved. We'll learn about kinetic energy in chapter 8. You don't need to know anything about it in this chapter, only to know that in an elastic collision, more stuff is conserved than in the other types of collisions. But I'm not going to ask you to do any math with it now or even later, really. Perfectly elastic collisions are extremely rare. We have some things that we say are approximately perfectly elastic collisions. Pool balls bounce off without hurting each other, without damaging each other. They do generate a small amount of heat, so they are not perfectly elastic either. But we'll do problems involving pool balls, and you'll be expected to assume that that's a perfectly elastic collision. The gas molecules we think are elastic collisions because otherwise they'd quickly do a lot of collisions and lose their energy and all end up on the ground, and we wouldn't have a very thick atmosphere, and that would be unpleasant. The other type is the inelastic collisions. Momentum is still conserved. Momentum is conserved in all collisions, okay? That's one of the main principles to appreciate. But in an inelastic collision, the objects stick together. So this is our bullet and our block. And there's a whole lot of gray area between the black of elastic and the white of inelastic. There's a whole bunch of gray. And that area we call imperfectly inelastic, where the objects don't stick together, but they do damage one another. And that's imperfectly inelastic. The reality is, it doesn't matter for our purposes what type of collision it is because momentum is still conserved. Well, I shouldn't say. It does matter because if it is an inelastic, perfectly inelastic collision, they are stuck together and you don't have to worry about two velocities afterwards. You only have to worry about one because they're stuck together. The problem will usually make that clear by asking, like it did with the bullet and the block, what's the velocity of the bullet and block? Or what's the velocity of the block with the bullet in it? Afterwards, it'll usually try to make clear that they are stuck together. So examples of inelastic collisions, cars that crash together and get tangled with one another, that would be an inelastic collision because they're stuck together. The bullet block one we just did. Here's another picture of a bullet block one being done where they're stuck together. Train cars that have, those couplings on them that cause them to hook together when they collide with one another. That's a favorite one in physics books to talk about, the train cars colliding. And a properly done football tackle, you wrap the guy up and you hold on. And so now you are stuck together after you've attempted to tackle the person. Maybe you haven't totally stopped moving yet, but you're now stuck together because you wrap him up the way you're supposed to. A few other minor issues that we're going to talk about here before we are done, which we are very close to. Although we allow internal forces, right? The two cars crash into each other and they exert force on each other. We can't have any external forces. If we have external forces, then we don't have a closed, isolated system anymore. We have some force from the outside delivering an impulse, and that means the third law force pair, right? The force that pushes back on that object, it's giving its impulse outside the system because it's pushing on something from outside, and therefore momentum is being transferred out of the system and we don't have conservation anymore. So we're allowing internal forces between the objects involved, but no external forces can come in from outside of our system, or else we lose our momentum conservation and we can no longer assume that the momentum before equals the momentum after. Again, this is similar to our discussion at the end of the last chapter about Newton's third law. This is how space works, right? Momentum conservation is how we move around in space. If you want to go one direction in space, you got to throw something the other direction. And Newton's third law and momentum are very closely linked principles, but here you see the astronaut with the bigger mass moving backwards slower because he threw his oxygen tank at a higher velocity forward. And so this is what we sometimes call an explosion problem, where maybe the astronaut and the tank were both not moving to begin with, and then he throws the tank and now they're both moving, but in opposite directions with opposite momentums. So you started out with m plus m times 0 equals 0, and now you have, say, 100 times -5 and 20 times, I can't do the math in my head, 250, whatever it is, and positive, so that those still add up to 0. So we call them explosion problems. You can also have the situation, again, if we had been in class, I would have taken two cars on my low friction track, I would have rolled them toward each other at the same speed with the same mass, and they stick and immediately stop because you have positive 10 units of momentum and negative 10 units of momentum. And when they stick together, that causes them to have 10 plus -10, 0. And that's one of the examples you'll do when you do your lab on momentum on the website. But an explosion problem is the opposite of a total stop problem. And, you know, it gets complicated in 3 dimensions. You got pieces flying in all directions. We're not going to do 2-dimensional problems. There might be one in your homework. If there is, you're allowed to skip it. We're not going to do 2-dimensional problems in this class. They're too involved, too complex for us to handle. But the reality is the momentum is conserved in both directions, and you can use sine and cosine to break it down and do it just like we did in chapter 4, the x and the y parts separately. But the upshot is that's why there's no safe place to stand when a grenade goes off, because for every piece of shrapnel that flies away from you, an equal amount of momentum has to come towards you. And so you just want to be far away from explosions. Again, this is why guns and cannons recoil, because we shoot the bullet or the buckshot or whatever out with a large momentum, and therefore the gun has to recoil with an equal momentum. Much less velocity because more mass, very typically, but still the same momentum. So you see this rope tied to the side of the ship that runs along behind the cannon, actually through the back of the cannon, and tied on the other side. That is so that the cannon, when it recoils, doesn't go flying across the deck and crush everybody behind it. That rope is designed to stop the backward momentum of the recoil and prevent it from causing harm. As I already said, we're not going to do the 2 dimensions, but you can do them by splitting them into vertical and horizontal components and treating those 2 conservations separately. So that's the end of the momentum chapter. We'll be back for chapter 7 on Thursday.